Right? So there should be more flexible management of those. The second one is that they have one IP address for each machine. This actually makes things more complicated. And on the other side, regarding the good part is that allocations actually are useful. So they do the cluster management. That is more useful than you just do the management for each task. So there are many others they learn. So they are doing more. Right? The second one is what we should pay special attention. Right? So Kubernetes is open source uh, and is to sell public cloud infrastructure. Right? So that was originally uh, targeted for, as we see here, like Google, if they want to sell the resource in Google Cloud, right? They can use Kubernetes. But now it's more than that, right? Even for private cloud, right? For Google's own data center, they will use this one to manage their resources. Right? This is the container-based computing versus the traditional like virtual machine-based computing. Okay, the second one, so for the following ones, I will go quickly so that we can still have some time for the uh, blockchain basics. Right? So, so what is a fair share right, of resources? Right? Let's say if we have three users, right, each represented in a different color, right? Here, if they want to share the CPU resources, then the solution is straightforward, right? Each one just get 1/n of the shared resource. In this case, each one get 1/3. The generalized is that uh, it's a this is an equal share, right? It's generalized by max-min fairness, means that we want to maximize the minimum of the want. Right? For example, if user one wants no more than 20%, right? Then you can give this user 20%, and then the other two users to they can each get 40%. So we can further go to the weighted max-min fairness. If the user one has a weight one, user two has weight two, then user one get 1/3 of the resource, while user two get 2/3, right? Those are all for single resource allocation, right? So as we move to multiple resources, like both CPU and memory can be the system, the bottleneck for the jobs, right? Some jobs, they are CPU bound, some jobs are memory bound, right? So this makes it more important, right? So the max-min fairness for single resource, right? The first is the sharing incentive. Basically means that the users won't be worse if they share the resource, right? In this one, versus they just get 1/n of the resource and use it exclusively. Second one is a strategy proofness, means that users don't have incentive to tell a lie, for example, to ask for more resources than they actually need. So those are the two properties, very important. Of course, there are many other properties, but those are two very important ones. Why? Because if they don't have sharing incentive, they won't share. If they have some incentive to lie, you actually don't know what the system will look like. Okay, so it's not enough for multiple resources, right? So this is a figure showing the tasks, right? Their demand. for CPU and memory, right? So each circle responds to a task, right? The blue ones for maps, while the orange or reddish, this one is for radios. The horizontal axis is the memory. The vertical one is for CPU. As you can see, they can be very different. Some jobs, they really need a lot of memory, but not much CPU, while there are others, the opposite, right? Which means jobs are not the same. They're very different, the tasks, right? So if you just use one resource to do that, then it's not sufficient. So, so those two properties that won't hold if you just do some simple extension. There are additional properties like NV freeness, which means a user should not prefer the allocation from another one, right? And the Pareto efficiency means that we cannot improve the allocation of a user without hurting at least another one, right? So the opposite is that if you can find a way to improve the situation of a user without hurting others, then you should do it, right? Because for the system, it's definitely get better. Okay, now let's pay attention to this one. So this is an example of multiple resource sharing, this allocation, right? So for the next, not the quiz we will do next Tuesday, but for uh, future quiz, like for future quiz, right? So we will basically ask you similar questions to say whether you are able to do the multi-resource allocation. Okay, here, let's consider there is a cluster with 9 CPUs and 18 gigabyte memory. This is a total system resource. And the user A want 1 CPU and 4 gigabyte memory for each task. User B wants 3 GPU and 1 gigabyte memory for each task. Right? So basically speaking, user A need more memory while user B need more CPU. Right? So in order to do the allocation, we first need to decide the dominant resource for each user. So in order to do that, you want to first normalize the user's demand, right, by the total resource. In this example, user A needs 1 CPU, and the system has 9 CPU in total, right? So user A wants 1/9 of the system resource on CPU, and 2/9 of the system resource for memory, right? It's 4 gigabyte divided by 18 gigabyte, right? So compare these two, user A wants more memory, right? Normalize the memory for this, so that its a dominant resource is memory. Similarly, you can get for user B. Right? User B needs 1/3 of a CPU, system CPU, and only 1/18 of the system memory. Therefore, user B's dominant resource is a CPU. So they want to equalize their dominant share, meaning that if we use X to denote user A's number of tasks, and use Y to denote number of tasks by user B, then we get this equation. 2/9 times X equal to 1/3 times Y. Right? And we also have the resource constraint, right? Because you sum them all the CPU resource and the memory resource, they should be less or equal to. And so basically now, from the equalizer of the domain share, you can get the x should be 1.5 times of y. And then you put them in, you get the constraint, right? And then you try to maximize x, which at the same time also maximize y. You get x equal to 3 and y equal to 2. It's the largest you can do. Right? Therefore, user A can get 3 tasks. User B get 2 tasks. And the resource allocation is that user A gets 3 CPU, 12 gigabyte. User B gets 6 CPU and 2 gigabyte of memory. Okay, so as I told you, we may ask you maybe multiple questions to test whether you can do the multi-resource allocation, right, as we do here. So any questions? Well, LEQ is less or equal to, because you sum the total resource you allocated, that should be less or equal to 1. I recommend you guys to do it by yourself now, to see whether you can go through the process and get the same answer. Okay, so hopefully you all get how to do this one, because this will be asked in the next quiz. Actually, the second quiz. Okay. Right, so there are other ways to do the allocation, right? So yeah, I want to go over those ones because you may get confused about this one. Right? So this is what you need to do, the domain resource fairness. And it satisfies all the constraints and give all the properties. Right. So the drawback of this one, so this is allocation is tenuously, not over time. Right. Also the uh, so yeah, so in this case, user don't have the uh, opportunity to define their dominant resource. Um, let me see this part. Okay, this is this allocation. This is scheduling. Okay, so the last two are optional. Yeah, if you're interested, you can look at those, but let's continue with the blockchain technology. So the key part I want you guys to master is that how to do the multi-resource allocation, as we just showed. Okay, now let's come to blockchain basics.